Good day, friends. Today I'll be talking about ruler and compass constructions. Rather, the limitations of ruler and compass constructions. Okay, so there are facts which are known from the ancient Greek civilization from the time of Euclid that some constructions are impossible. Now we need field theory and its extensions to prove that those constructions are impossible. So let us start with impossibility 1 due to Wurzel. Suppose you are given a cube, a unit cube of each side of unit length. Using that length, can you construct the length of a cube with volume 2? So you need from unit length, you need to construct root cube of you need to construct the length root cube of 2. So we need field theory to understand why it is impossible by ruler and compass. Then impossibility 2 is trisection of angles. I mean, in general, it is not true that no angle can be trisected. Suppose you are given the right angle triangle 90 degree, so you can readily construct a 30 degree you readily construct a 30-degree angle and can trisect the angle. But for some special angles, it is not possible. So we took up pi by 3, which is 60 degree, and proved that it is impossible using ruler and compass. Then suppose your impossibility 3 is about you are given a circle and you are supposed to draw a square with the same area. Now that is also impossible. Okay, to prove these impossibilities, let me start with ruler. What is a ruler? Given 2 points, you can connect them using a ruler. You can draw a line segment connecting those 2 points. That's a ruler or straight edge, no marking. And what is a compass? Given a point and a certain length, you can draw a circle using the radius as that given length. So that is compass. Okay. So starting from there, what are constructible points? Okay. So you are starting with several points P0 in the Euclidean plane, and you go on adding the points R1, R2, dot up to Rn in the Euclidean plane, such that each time you take P0 union R1, R2 up to Rj minus 1 and construct the point Rj using ruler and compass. So those are the constructible points. So I have a sample here. Midpoint of a line segment is constructible, which is easy to prove. Easy to prove using uh, ruler and compass. But to understand the limitation of ruler and compass constructions, we need to know about field and field extensions to find the limitation of ruler and compass constructions. So we need to know about group. So a set of point G with a binary operation plus is a group if it is closed. G plus H belongs to G for all GH in the group. It has an identity element 0 such that 0 plus G equal to G plus 0 equal to G. It is closed under inverse. So if you have a point G in the group, then minus G is also there, and it is associative. G plus H plus K equal to G plus H plus K. So that's the definition of a group. Real line rational points are example of groups with 0 as the identity element. Then we need the concept of subgroup. So H plus is a subgroup of G plus if H is a subset of G and H plus is itself a group. Okay. So real numbers form a group and rational numbers is a subgroup of it. Then we need the concept of normal subgroup. So given a point G in the group for a subgroup H, GH is G times H, and which are called left cosets, and H times G, this set is called right coset, and in N is a normal subgroup. If N is a group, N is a subgroup of G, then left cosets and right cosets are same. G multiplied by capital N is same as N multiplied by capital G. If it's abelian, then any subgroup is normal subgroup. Then we need the concept of ring. So G with two operation plus and dot is a ring if G plus is a group, and if I take away the identity element, the null element, the identity element under plus operation from G, then it's a group, but it need not be closed under inverse. Okay, and then the second operation is distributed over the first. G times H plus K equal to GH plus GK. So under these rules we get a ring. We have ring of polynomials where it is not closed under second operation. But when we talk about field, we have a set of points G and plus and dot, two binary operations. Then G plus is a group, G minus 0 dot is also a group, and second operation is distributive over the first. Then we get a field. That's called a field. So what is field extension? Suppose K is a field in the real line, and we consider an irreducible monic polynomial. Monic means the coefficient of the maximum degree is 1, so that is monic polynomial, and irreducible is it cannot be factorized. That is irreducible. So if we have a monic polynomial MT having the 0 alpha outside K, then we can extend the field K using alpha in this way. K alpha equal to A plus B alpha, where A and B are in K. Then K alpha is again a field, and it's called a field extension, and the degree of the extension is the degree of the monic polynomial. I omit the proof. So this is the technique of field extension. Suppose you start with a set of points P0, then the field, we need to know the field generated by P0. So we first define G0 as alpha t plus beta s, where alpha beta are rationals and T and S are constructible, are the set of belongs to the set of initial points. Then we define the field generated by P as T by S, where T and S are in G0 and S not equal to 0. So that's field generated by a group of starting point. Now we need to go to field extension. Suppose we have field K j minus 1 over P0 union R1 R2 Rj, then Kj is the field extension of Kj minus 1 using the point Xj Yj. So this sets the set of points in the fields are increasing. So we start with K0, the initial field, then we do the extension K1. K0 is a subset of K1, then K1 is a subfield, is K2 is extended by is the extension over K1. Kn minus 1 is an extension, Kn is an extension over Kn minus 1. So K0 to K1 is called a tower. Now we need to prove the claim that the points we are extending with Xj Yj over Kj minus 1 are zeros of a quadratic for ruler and compass. I am not going to the proof. So we start with a set of points K0 and go on adding constructible points by ruler and compass. We get K1, then we get K2. Finally, from Kn minus 1, we get Kn. But each time the degree of extension is the degree of extension, or the power for the ruler and compass construction is 2. I have the proof here. For ruler and compass construction, the monic polynomial has degree 2. So this is the limitation of ruler and compass construction, that as the construction progresses, fields get extended and extended with the degrees, and the degrees get multiplied only by powers of 2. So constructible points and its extensions, the fields extended only have power of 2. So that is the limitation that needs to be explored to prove the impossibility of ruler and compass constructions. So let us start with doubling the cube. So we start with 0, 0 and 1, 0, and we can draw this length of unit length. To draw a root cube of length, a root cube of a length equals to root cube of 2. We need to extend by the monic polynomial t cube minus 2 equal to 0, and but the extension q alpha over q has the degree 3, which is impossible for ruler and compass construction. It allows the extensions only of degree 2. So when it comes to degree 3, the ruler and compass construction becomes impossible. So doubling the cube is impossible. Then trisecting the angle pi by 3. So pi by 3 is constructible. We need to construct pi by 9. So we need to construct a point alpha 0 where alpha equal to cos 2 pi by 9. So here the monic polynomial is beta cube minus 3 beta minus 1 equal to 0, which comes from the equation cos 3 theta equal to 4 cos cube theta minus 3 cos theta. So if we could trisect pi by 3, the field extension needs to have degree 3, which is impossible for ruler and compass. So trisecting pi by 3 is impossible. Then squaring the circle, we need to, from the set of rationals, we need to extend the field with using pi. So q pi is an extension over q, but in that case, pi needs to be solution of a polynomial of q, which is impossible because pi is transcendental. It's not an algebraic number, so pi is never a root of polynomial with rational coefficients. So that proves squaring the circle is impossible. So this is from the book by Professor Ian Stewart on Galois theory. I am trying to understand why a quintic is not solvable, why a general quintic is not solvable. Maybe I will give that talk someday. Thank you.